Hi, today I'm going to talk about lecture 3, which is about data structures. Okay, so let's summarize this set of lectures. So in this lecture, professor talks about various basic data structures, and he basically covers queues and stacks, and we'll see why he covers these basic data structures and how they're implemented. I think that he has a very neat reason for that, and he also at the end talks about bags. While doing so, he talks about their implementations in Java, and also talks about some key considerations for the same. So let's talk about, I think we all know what stacks and queues are. Stacks, for a stack, you push and you pop, so the things get inserted at the head, and you when you pop things, you also get the thing that is at the top of the head. For a queue, you are pushing or enqueuing things at the tail, and you're popping or dequeuing at the head. That's what you're doing. Okay, so the way I think about it, it's first in, first out, and last, FIFO and LIFO, that is last in and first out. Yes. So I said last in and first out. Okay, so I think so LIFO, stack is last in and first out, and queue is first in, first out. Correct. So this guy got it in the first, and it came out at the first. So that's what it means. So remember these acronyms: LIFO and FIFO. FIFO is for queue and LIFO is for stack. Okay, so there's some things about interface. Okay, so he talks about that for a client, ideally the interface should be the same, so that I can use various data structures without really changing the client code much. So that's an neat point. So the basic idea is designing to the interface and not the particular implementation. If we can achieve that, that's always a good goal to have. So let's look at this. We already spoke about the stack, and we know how the API looks like. Okay, talks something about once again the test client that needs to be used. Okay, so now the implementation. So there are two ways we can actually implement a stack. One can be through a linked list, and in a linked list, the linked list is a basic data structure. So I'm not actually going to cover linked list and arrays. I just assume everybody knows that. If not, you can just go ahead and refresh it. But in the idea, the linked list is you have a pointer pointing to the next node, and for array, it's a contiguous set of array blocks, and you don't have to worry about pointers because they're kind of contiguous to each other. But in the linked list, they can be anywhere, and the way you traverse a linked list is navigating through the pointers. Correct. So let's look at it. If you are implementing a stack through linked list, what would you do? Okay, so this is the basic idea. When you're trying to insert something, what you do is this is, let's say, the current first node of the stack. You have a pointer that says, okay, this is old first. You create a new node with first, and you point and you update the value of this first node to the value that you're trying to push to the stack, and then you point this node to the old first. That's the basic idea, right? So the first becomes this new first. So when you try to pop, you can just remove this first. Correct? That's the idea. Okay, so we spoke about that, and now he covers a little bit about the in terms of how much memory would something like this need. And he definitely talks about the node class, which actually stores the value. It may be an int or a string or whatever, and then he talks about, okay, that you need 8 bytes reference to the next node, reference to the actual string or the int value, some class overhead, and some object overhead. But you will end up with 40 bytes per stack node. Now let's look at an array implementation. Now this is more interesting. In this case, what it means is that let's not worry about the size, okay, because as you know that you may you may continuously go ahead and push things without popping, so you'll have to deal with overflow, but we'll talk about that later. The idea here is that push will add an item at the end of the array, and pop will remove the item at the end of the array. So the way you will deal with push and pop is knowing what's the current n value, where given the capacity right now the array is 10. What it means is the array can at most hold 10 values, but we'll deal with increasing capacity dynamically. Now the interesting point here is that why would you, let's talk about, I'm not going to look at the code as such, but the interesting thing is, why would you use an array instead of a linked list, right? They kind of look the same. Looks like linked list doesn't have the pros and cons, the cons of the fixed capacity of an array. Then why would you ever worry about arrays? Think about that, but we'll actually cover that later. So this is the code. Some points about null items, that the moment you have dereferenced or popped an object, it missed the array still holds reference to it. So to make sure that the garbage collector does its job, you may want to explicitly set it to null. That's the basic idea. Sn is equal to null, and this thing is called as loitering. It's kind of sitting around the garbage collector, is not really recycling that memory. Okay. So desizing arrays. Okay. So I think this is an interesting concept about amortization, and also we should talk about amortized analysis, and I'm going to cover this in a separate video. So for now, just take the word for it, but I am actually going to spend some time, maybe not in a separate video, but at the end of this video about it. Maybe I should do it right now. Let's see. So the interesting thing here is that how do you deal with dynamic capacity? You may actually grow and shrink the array all the time, right? That the moment you start with at the degenerate and extreme case, you can imagine that you start with 0. The moment you have to, the moment somebody tries to push it, you increase it by 1, right? Somebody tries to push it again, you increase it by 1 again. But now that is going to be tricky, because every time you increase, you increase it by 1 means you are creating a new array, and you have to now copy the contents of the old array to the new array. So it means you're doing a lot of copying, and as you can imagine, given this n elements that are inserted, you will actually end up copying it 1 plus 2 is equal to n, which is order n square. So that is actually very, very bad, correct? So what do? So you, instead of just increasing it by 1, you double it every time the array reaches the capacity. So that's interesting. So now how does that help? Why do you want to double it, and how does that help? And is that the same as n square or what? But turns out it is not. It's actually order of n, and we'll look at it later. Okay, so this is an interesting thing, but let me just spend maybe right now, I think maybe is a good time to just talk about amortized cost and how do you analyze that. And for that, I think Professor, in the interest of time, doesn't go into detail, but I think this is something that we should understand it really well. So let's do that. Okay. So what I did is I went ahead and I just found some lecture notes from CS61B. It's a course offered in Berkeley, and I think that was really good. So I think that the lecture notes there were really good. So that's what I'm using right now. Okay, so it's CS61B from Berkeley. So I think so he has the professor has a very neat way of explaining how do you analyze amortized cost. What that means here is that, let's say in terms of an array, you are going to, if you want to do a pop or a push, it takes constant amount of time, right? It's all O1. At the end of, if you want to pop or push, you immediately know what's the end and you go ahead and perform the operation. But at times, so what it means is when you're doing n times, it's order n. But at times you have to do this complete copy, which is order n itself. So now when you look at the total cost of the algorithm, what is it? How do you analyze that? So the basic idea here is, for a particular n, you figure out what is the total cost and then divide it by n. So let's look at that, right? So we spoke about order 1. Now this I think is the math. So let n be the number of items in the hash table, and let n be the number of buckets. Okay, so he's using it for the way for explanation of amortized cost. He uses hash tables, and in hash tables, as we know, you can, let's say you have n buckets, correct, and there are n items. Now you can go ahead and you don't want to have the same, you can only have one key in each bucket, right? So the idea here is that every time if you already have all the things filled, then you double the size of the table. It's kind of the same, right? So just imagine this: instead of hash table, you are implementing a stack in an array, and the moment you have filled n, then you double it. So it's the basic same idea. So, and the load factor is, and this is the idea, right? The load factor of n by n is always less than 1. So that's the basic thing. Now, what happens here is that, let's say you are doing this for n such elements. So how much time in terms of cost are you taking for this resizing operation? How much time does it take? The first time it takes 2, the second time it takes 4, the third time it takes 8, because you're doubling, right? So every time, it's only when you have 8 will you actually do the copy. You're not going to do the copy for 6, 7, etc. So you're doing this for this entire series, and somebody will immediately know that this is a geometric progression starting at 2, and the factor is 2, r is equal to 2 here, and if you just do the math, this comes out to be 2n, right? You can actually see that even in other ways. So the idea here is that it would be n, so the total cost of pushing would be order n, and then the total cost of resizing is 2n. So the total cost is order 3n. What that means is it is still a constant, it's still a factor of n. It's not n squared anymore. That, I think, is the most important fact here, correct? So, and that's what he says, it's 3n. I think we kind of get to that, the same thing. And that's that, I think. So what that means is no longer exponential. So that's the way, that's the analysis of the amortized cost. Now, in the shrinking of array, in the same way, you do not want to shrink every time it becomes null for the first time, right? Like you do not want to, if n is 5, in the moment something becomes null, you don't want to set n to n minus 1. You don't want to do that, because again you'll pay a lot of penalty. So in this case, what you're trying to do is, okay, so instead of, he says that you can do it 1/2 full. As you went double, you can do 1/2 full, but instead of that, you actually do 1/4 full. Okay, so it's a little bit tricky. So, but the basic idea here is why you don't want to do 1/2 full, because you can imagine the degenerate case, once again, worst case, where you just go 0 1 0 1. So you're doing if it is half, you're constantly pushing and popping, right? So you're constantly, every pop, if there's just 2, every time you pop, it becomes half, so you try to shrink. And then the moment you try to push again, it is double, so you again, you have to resize. So you're continuously resizing. You want to avoid doing that. So that's the idea here. You do it when it is 1/4, and the invariant array is between 25% and 100% full, right? As you're pushing and popping things around. So that's the basic idea here. Okay. So that's it. I think, is this the last slide? Looks like this is the last slide. Oh no, there's still some more slides. Sorry. So queues. So we spoke about stacks. Now let's look at queues. We already explained queues. First in, first out. First in, first out. Correct. So as things are getting in, they will get out first. Right. First in, first out. So I'm using the term push, but you get the idea. It's push, because as you can see here, push and enqueue are kind of the same thing. So you're pushing from the tail of the queue, and you're popping from the head of the queue. Okay, and I think the main reason you're doing NQ and DQ is so that somebody who's using it knows that you have a queue and not a stack. I think that's a good thing. It's not a bad thing. Maybe at times you may not want somebody to know. Maybe in that case it's not a good thing. Once again, you can, I'm not talking about that. You need first and last, and you can figure out the linked list implementation for this, and you can also look at the array implementation for this. So once again, I just skipped it. I think that you'll be able to figure that out. In terms of generics, I think here professor just explains templates, generics, those kind of things. Supposedly, at some other time Java didn't have it. I think C# got it before Java, and then Java implemented it. The idea here is you don't want to have a stack of strings, stack of URLs. You can just have one stack of type T. If you know C, C++, C#, Java, any of these languages, you understand what generics are. Okay, so it's parameterized, and it talks about how do you do this. He explains a little bit that you can't really do that. Generic array creation is not allowed, unfortunately, in Java. So you have to do this, and you have to do cast, which is kind of the ugly cast. That's what he calls it. I think that's a neat. I think he's very good. I think he the moment he sees the code, he knows what's good code. I think that is really good. And he makes some fun about it, for the Java designers, that they should feel very bad about it. Okay, so that's it. He talks a little bit about how Java does how Java handles primitive types for int and integer. They do automatically casting and things like that, or boxing and boxing. That's what it's called. So we looked at generics. He also talks about iterators. This is basically things that will help you do a for each, and it's in Java it's the iterable interface. That's the basic idea here, and something some syntax that you need to worry about when you're writing and trying to implement an iterable for a particular type of object. Okay, so it's some more implementation details, not too much worried about it. And once again, you can do it both through linked list and through an array. For each of them, how do you figure that out? That's fine. And bag is something which is which is the most kind of, I would say, basic, that you're just adding and removing things. You're just adding things, okay, and then you're just iterating. You never remove. Okay, so that's the idea. And how would you implement something like that? And implementation is without pop and without DQ. So that's the basic idea. Applications. He talks about various things. Okay, and okay, so poorly designed API. He talks about okay, you should have a class that does only one thing and does it really well, and things like that. And he also talks a little bit more interesting things and why we should use not the Java implementation but his implementation, and we'll get to it very soon. Okay, so here's the idea that if you pick up, when you're trying to do, for example, the n/n percolation system, right? We learned about this in the previous lectures. Then you can, for you to be able to pick any I and j at random at constant time, you want an array implementation. Now instead of that, you use an array list. Internally it uses a linked list. So for you to go to I and j, you actually spend order n. It's no longer constant. You're actually spending order n square, correct? So that, as you can see, they will increase the total time by a factor of n squared. So the array implementation, which is order n square, and the linked list implementation will actually be order n raised to 4. So you can imagine things don't work that well. And somebody realized that, turns out although my algorithm, my thing is correct, but I'm using a very poor data structure, and it is just taking far too much time for me to complete. So that's the idea. So it talks a little bit of some applications of stacks, which is fine. Okay, I'm not going to go about that. I think you guys know for you can use this all for for various things, parameters, okay, etc. Okay, so these are the things. I think there was at least one slide. I'm trying to find that slide. Did I gloss over it? About why would you prefer an array to a linked list? I think that was a very good slide, and I'm trying to find that. Maybe it's in the next chapter series, so maybe it's in the next set of lectures. If that's the case, it's okay. But let me spend a minute and to see if there is okay, here's the thing. I think this is an important slide. Sorry I missed that, but I was quickly going over it. So you could either choose an array or a linked list. Which one is better? The important thing here is that There are two things. I think there are two things. First is for array, every operation takes a constant time in worst case. For linked list, correct? It's always the same. It does use extra time and space to deal with links, right? Because when you're trying to navigate and things will be slower. Here, okay, every operation, the constant time is the same, but there is much less wasted space, right? There is no pointers, nothing to be dealt. And the most important thing is when you're doing with multi-dimensionals end by end, the thing that we saw about at the end, you definitely want to use an array instead of linked list. So that's the basic idea. Okay, so this was the lecture about the basic data structures. We'll look at sorting algorithms in the next lecture. Thanks. Bye.